All right, so we've learned about displacement, angular velocity, angular acceleration. Now we want to talk about the angular equivalent of force. Okay, that's called torque. So the angular equivalent of force is torque. And we still follow a pattern, right? This is the Greek letter tau. So again, it's cool because we always use Greek for angular things. Okay, so all right, so we're going to talk about torque. Sorry to say this, but torque is much more complicated than just force, like we learned a long time ago. So here's a fill in a blank. A force causes a linear acceleration, right? You better know that by now, because F equals ma. So force causes an acceleration. But now I'm using the adjective so we don't get confused. So a force causes a linear acceleration. Well, therefore, a torque causes an angular acceleration, right? Doesn't that totally make sense? So, I mean, see the pattern? F equals, force is a proportional acceleration. Torque is proportional to acceleration, but it's angular acceleration, which makes perfectly good sense. Okay, now, have you ever heard of a torque wrench? So these are called torque wrenches. They measure torque. So if you're, tightening up a screw, they measure how much rotational force you're applying. Why would you want to do that? Well, here's my bicycle. Okay, so I'll blow this part up. So it says maximum torque 8 Newton meters. We'll talk about the units in a minute, right? So what does it mean? It means if you tighten this bolt, you don't want to exceed 8 Newton meters or you might break it. So that's why you use a torque wrench, so you don't exert too much torque. Okay, all right. Here's a question for you. A disk is rotating about an axis. In order to maintain a constant angular velocity, a constant torque must be applied to the disk. Ignore friction. I'm going to give you a hint. Here's your hint. Okay, so pause your video and answer the question, please. Okay, so we're back. The answer is false, totally false. Come on. In order to maintain a constant angular velocity, you don't need any torque. Think about it. You're in deep outer space. You throw something. There's no external force on it. So what do you say? The acceleration is 0. The velocity is constant. It's the same thing here, right? It's the same thing here. Constant angular velocity, that means the angular acceleration is 0, so the torque is 0. Just like F equals ma. Exactly like it. All right, now we're going to look at a door. So unfortunately, this door is locked. So just pretend it's not. Okay. Can you? Okay, let's do it. All right. Okay, so let's say I want to open this door. So where am I going to press? Am I going to press here? Or am I going to press here? Okay, so you have to admit, if you're opening a door, it's much easier to rotate this door about the rotation axis when you press here as opposed to pressing here. Okay? Okay, now all right, so in other words, the torque, which is like rotational force, depends on not just the force, but where you apply the force. How about this? Okay, hold on a second. Hold on just a minute. Okay. All right. Now let's say, what do I do now? Oh, golly. Okay. Supposed to be quiet in this room. Now let's say, okay, normally I would push this way, right? Well, what if I pushed like this? Would that be any good? Right? If my force were in that direction? Totally waste of time, right? Okay, so what have we seen? So the torque depends on how much force where you apply it, and the angle. Thanks. Okay, so like I said, way more complicated than force, you know? Okay, so now this will hopefully make some sense. Okay, so now this is the top view of the door. So there's the hinge, which I'm going to call the axis of rotation. All right? Okay, so if I'm going to open the door, I'm going to push here, right? This is going to be very effective. That's not going to be so effective. That's going to be really difficult. This is going to be a total waste of time. So somehow, so there's the magnitude of the force, there's where you apply it, and there's an angle. So there's 3 factors with the torque. Wow. So we got to come up with some equations for this, right? Okay, so first we're just going to do the magnitude of torque. We're not going to worry about the direction, just the magnitude. Okay? So here's an equation you're going to see all the time. So the magnitude of torque equals the force times r perpendicular. What is r perpendicular? Okay, so hold on. Some people call r perpendicular the moment arm or the lever arm. You'll see that in the book. R perpendicular, moment arm, lever arm. So what is it? And I'll give you some examples, don't worry. So r perpendicular is the perpendicular distance. Here, sorry. So r perpendicular. So here's the rotation axis, right? So r perp is the perpendicular distance from the axis to where you applied the force. So here's the axis. Here's where I applied the force. Perpendicular distance from the axis to where you applied the force. So this distance is r perp. Okay, now let's get some demos here. All right. So here, okay, yeah, here it is, all right? So r perp, moment arm or lever arm, perpendicular distance from the rotation axis to the force, so to where you apply the force. I call it the force line. You'll see in a minute. So this is how you do it. Okay, let's look at F1. So this is the force, right? So we just extend it, and I call that the force line. So this line here is just an extension of F1. It's the force line. So r perp is the perpendicular distance from this line to the axis of rotation. And it's obviously this, right? It's the yellow thing. Agree? Here's the force line. Here's the axis. This is perpendicular right here. So you can see that F1 has a really, really long lever arm, you know? So you know, if this is really big, and this is average, it's going to have a big, big torque. So it's going to be simple to open that door, you know? Hey, what happened? There you go. All right? Okay, now, so that's F1. Let's look at F2. Now, who in their right mind would try to open a door like that, right? Well, why doesn't it work? Because here's the force. So just like before, you extend it however long you need to. Okay? So this is what I call the force line. The force line. Now, what is the perpendicular distance between the force line and the axis of rotation? It's 0. So that's why it doesn't work. Okay, that kind of makes sense. All right, let's look at F3. Now you figure it out. All right, so pause the video and figure out what is the lever arm or the moment arm or r perp for F3. Okay, we're back. So here you do it. Here we go. So here's the force, F3. So you just extend it however long you need to. Just extend it, doesn't matter. And we want the perpendicular distance.
Aloha. The leverage will be closing in 1 hour. The circulation desk will close in 50 minutes. The computer lab will close in 45 minutes. The media services will close in 30 minutes. All reserved items and laptops are due in 30 minutes. Mahalo.
Okay, so you extend F3, and then we want the perpendicular distance between this force line and the axis of rotation. So here it is. Ta-da! So it's kind of like a medium length, you know, medium length lever arm. It would, you know, it wouldn't be as It would be kind of hard compared to this one, right? Now, please you figure out the lever arm for F4. So pause your video and figure it out. Okay, we're back. So again, you extend the force vector. Extend the force vector however long you need to. Then you want the perpendicular distance from this line to the axis. Well, it's right there, right? It's right there. So that's a really short moment arm. So that means if this is really small, you know, for an average force, it's going to be really hard to open that door because the torque will be small, which is exactly what agrees with your experience. All right. Okay, so this is one equation for the magnitude of the torque. Let's find another one, okay, because it's nice to have more than one. Okay, so this is a blob, all right? This is some blob. I don't know what it is, a blob. And this is the rotation axis, right? So this is where it's going to, you know, it's going to rotate about this. Okay, this is the r vector, the position vector, the r vector. Here's the point on the blob where the force is being exerted. Okay, whoopee. All right. Again, this is just magnitude, right? Just magnitude. Okay, so again, the torque is the force times r perp. Okay, well, okay, here's the force line. So we extend the force line, and then r perp is the distance between the axis, perpendicular distance between the axis and the force line. So there it is, right? So you just multiply this distance in meters times this force in newtons. And that's why on my bicycle it said maximum torque, the unit was Newton meters, right? Newton meters. Okay, so that's how you can, that's one way, that's the first way, but we're trying to learn the second way. So let's learn the second way. Okay, so, you know, we can always decompose our vectors, right? We can do whatever we want to do. So we do it all the time, right? Ugh, what is that? It's supposed to be parallel. Whatever. Okay, so we resolve or decompose our vectors into a piece that's parallel to r and perpendicular to r. Okay, we can do that. And you'll see why. All right, so we do that. Now, so kind of ignore this now. Just ignore this. Just concentrate on this one, this F parallel, and F perp. Now, which force, which component, F parallel or F perp, provides the torque to rotate this blob around this point? Well, obviously, this is a waste of time, right? It's not going to do anything. So this is the one that provides the torque, F perp. Okay? All right? So we can say that the equation is F perp times this R. Okay, that's cool. All right, that's cool. But now, oh, that's it. Okay, all right. So there's two equations. There's F R perp and F perp R. That's pretty simple to remember, right? Okay. All right, now some questions for you. You're trying to open a door that is stuck by pulling on the doorknob in a direction perpendicular to the door. If you instead tie a rope to the doorknob and then pull with the same force, is the torque you exert increased or not? So pause and answer the question, please. Okay, we're back. The answer is absolutely not. Well, why? Well, because think about it. I mean, let's say the door's right here. You know, I'm pulling on it with a certain force, but if I put a rope and I pull, and the force is the same, the force doesn't change, the R perp doesn't change, so it's the same torque, right? Nothing has changed. Okay, you're using a wrench and trying to loosen a rusty bolt or nut. Which of the arrangements shown is the most effective in loosening the nut? List in order of descending efficiency. So we went the best to the worst. The following arrangements. So figure out which is the best, which is the worst, and arrange them best to worst. So pause your video. Okay, now remember, torque is force times lever arm. Okay, so the forces are all the same, right? So the only thing that matters is the lever arm, okay? And the lever arm is perpendicular distance from the axis of rotation. So which one has a bigger lever arm? Well, this one, obviously, right? Here's the force line. Here's the perpendicular distance between the force line and the axis of rotation. So this is the biggest. Okay, how about this one? This is the axis of rotation. This is the axis of rotation. Does this rod do anything at all? No, it's just like the rope in the previous problem. There's nothing, waste of time. So same force, same lever arm. So these guys come in second, tied for second. Now here, this is the force line. So this is the lever arm. That's the smallest, right? So this guy is the worst. So 1 is the best. 2 is the best. This guy. 2 is the best. These guys tie. 1 and 4 tie. And 3 is the worst. Make sure you understand this. Okay, let's do an example. Oh, yeah, there's a little subtlety we need to talk about. Remember we talked about angular velocity a while ago, and we said that if it was counterclockwise, omega was negative, and clockwise, omega is positive. Remember that? I think we actually used it with delta theta. I don't know. I don't remember, but I know we talked about it. That counterclock was oh my gosh. This is completely wrong. Gosh, completely wrong. Counterclockwise is positive. Clockwise is negative. Gee whiz. So I might not have said with the omega, but we talked about, it's kind of like this, right? You know, we talk about moving to the right is positive, moving to the left is negative. Then we talked about counterclockwise is positive, clockwise is negative. All right, simple as that. Okay, and it's also true with omega. All right, so counterclockwise omega positive, clockwise omega negative. You got to know that. All right, if you don't know that, you get the signs wrong. Okay, so we have to use that with torque. You'll see. So remember, clockwise, negative, counterclockwise, positive. Most people think it should be the opposite. Sorry, right? So counterclockwise, positive. Clockwise, negative. Okay, let's do an example. Oh, sorry. Okay, so here you have this beam, and you have an axis of rotation right there. And here's a force that's going to make it go counterclockwise, right? But here's a force that's going to make it go clockwise. So what we want to know what magnitude of F2 causes the net torque to be 0, so it doesn't accelerate at all. All right? And here's the tricky part. Okay, so we want the sum of the torques to be 0. That's what we want. So let's do it. Okay. So the torque is the force times the lever arm. So let's do the F2 first for no good reason. So here's the F2 force line, right? You extend that. Then the lever arm, perpendicular distance to the axis of rotation. So the lever arm is L over 2. Okay, so the torque is F2. Notice I left a space here on purpose. F2 times the lever arm, L over 2. Now, here's the thing that sometimes students forget about. This force by itself is going to make this thing rotate how? It's going to rotate clockwise. So you have to put a negative there because clockwise is negative. And you have to remember to do that. There's just no other way to explain it. Okay, so that's the torque for this guy. Now we want the torque for this guy. All right? So the first thing we do is we extend the force to get the force line. So we do that. So there's our force line. Now we want the perpendicular distance between the force line and the axis of rotation. There it is, right? Here's the force line. Here's the perpendicular distance from here to here. So there it is, okay? Perpendicular distance between the axis and the force line. All right, now, okay, so let's see. Well, hold it. Before we do anything, I mean, just looking at this force, only this force, it's going to make it go counterclockwise, so it's plus. So it's plus, okay, the force is 20 newtons. And what's the lever arm? Remember, the lever arm is a distance. It's not a force, it's a distance. Okay? So what is it? Well, this is the lever arm. So it's L. It's opposite, so it's sine. So it's L sine 45. So it's L sine 45 degrees. Now, this is a big deal, okay? The lever arm is a distance. Why do I keep saying that? Because some people, they don't realize that, and they would say like 20 newtons times. They would say that tangent 45 is this divided by 20 newtons. That's crazy, right? You can't mix up distances and forces, okay? So it's a distance. Okay. All right. All right. So solve for F2, so we put it on the other side. So we have F2 L over 2 equals 20 newtons times L sine 45. Okay? So what do you notice? Get rid of the L's. Multiply both sides by 2. And I promise you, when you do that, you get 28.3 newtons. Okay, so there you go. Now, we're going to do more of these torque problems in a future chapter, but, you know, you got to know how to do it. Yeah. So I just put this here just for your reference, so you can look at it later on. Make sure you can do these torque problems. They're super important. Okay. All right. Let's talk about something completely different. Okay. So, way back at the beginning of the semester, we said that we were always going to talk about the particle model, right? And so whenever we drew a force diagram, you know, we just draw it like that, right? Even if it was a car, we didn't care. We just draw a dot, the particle model. Well, now we're going to expand our horizons, okay? So let's look at this, for example. This is not a particle. This is a large number of particles, right? A large number of particles. And if I threw it, okay, you know, every molecule had a completely different trajectory than every other molecule, right? I mean, spinning all sorts of crazy things. However, there's one point on this marker, which is called the center of gravity. There's one point which acts like the one point undergoes perfect parabolic motion. So in other words, if this thing were a point particle, the center of gravity acts just like that point particle. Okay? So in other words, you know, like a point here, it certainly doesn't go in perfect parabolic motion. It goes all over the crazy place. But if we found that one place, the center of gravity, it would undergo perfectly parabolic motion. So the center of gravity is that one point that acts as if all of the mass of the object is concentrated at that one point. Okay? It's also called a balance point. How do you locate the center of gravity? Well, here, it's pretty simple with a ruler, right? It's the balance point. How do you locate the balance point? You know, just 50 centimeters, right? It better work. Yeah, there we go, right? Right? So if I threw this meter stick anywhere I want to, that one point, the center of gravity, again, you assume all the mass is concentrated there, would undergo perfectly parabolic motion. So here's a really cool slide. If what I said didn't make any sense, hopefully this will make sense. Okay, so the center of gravity is one point on a hammer. So you take a hammer, you throw it, and put a spin on it. I don't care what you do. So this one particular point, again, it acts as if all of the mass is concentrated there. It undergoes perfect parabolic motion. Perfect. Okay? So that's kind of cool. Okay, where do you think the approximate center of gravity is here on a wooden baseball bat? So pause your video and vote, please. Okay, I hope everybody said D, right? Because most of the mass is concentrated over here. So I think the balance point is somewhere over here. And I brought a bat. This is not wood, it's hollow you know, metal. So let's see. Okay, somewhere there. Okay. All right, but here's one for you. Here's a donut. Where do you suppose the donut center of gravity is? Right here. All right, so the reason I showed you that photograph is sometimes the center of gravity is not, it's not part of the object. Okay, it's outside the object. All right, we got to figure out how to calculate these center of gravities. So this is just the x center of gravity. So all we're saying is there's one dimension. Okay, so the x center of gravity. Let's say I have a whole bunch of particles or a whole bunch of masses or something. Just a mass. Okay, so first you have to choose an origin. So here's your origin. So it's just the mass of particle 1 times the distance of particle 1 plus the mass of particle 2 times this particle 2, on and on and on, divided by the total mass. This is too much trouble to write it like that. So you say 1 over uppercase M. Uppercase M is the total mass. And this is your sum sign you've seen a million times before. Just MIXI. So that just means M1 X1 plus M2 X2 plus M3 X3, on and on and on and on and on. Okay? So here's some nice pictures. So if this mass is approximately the same as that mass, don't you think that the center of gravity is going to be in the middle? It's the balance point, of course, So we'd calculate by just using that formula. On the other hand, if this mass is tons, well, not tons, if this mass is bigger than this mass, the center of gravity is going to be closer to the big mass, right? You just use that formula. All righty, so I have a problem for you to do. Okay, the moon orbits Earth. Very good. They are separated by a center-to-center distance of 3.85 times 10 to the 8th meters. Earth's mass is whatever, and the moon's mass is whatever. How far does the center of gravity lie from Earth's center? So the Earth's center is the origin. So everybody, pause your video and figure it out. Okay, so let's do it. All right, so X, center of mass. And again, the important thing is, well, let me just write the equation. So there's only two particles, right? Or two objects, the Earth and the moon. So we have mass Earth, X Earth, plus mass moon, X moon, divided by the mass of the Earth, plus the mass of the moon. But the important thing is, what's the origin? The origin is from the Earth's center. So X Earth is the center of the Earth, the origin, to the center of the particle, which is the center of the Earth, so it's 0, right? So this is 0. So that just wipes out. So we just have mass moon, X moon, over the total mass. So that's all you have, okay? And so if you work that out, I'll let you do that. 4.67 times 10 to the 6th meters, okay? Because this is just 0. That's all. Okay, let's do another one. Actually, let's quit. Darn.